Yeah, thank you for the kind introduction. I'm super excited to be here. It was a fantastic introduction into data and AI and all that cool stuff we will be talking about. And of course, I'm very excited to meet Brad Gammons again, right? We worked for many years together in IBM. Super excited. So the title of my presentation is AI for Critical Infrastructure. And I want to start, I like always to step back a little bit and ask a very simple question. So why should we even consider AI, something so virtual and abstract for something as physical and real as critical infrastructure? And to answer that question, I think it's helpful to go back in time. Over the last 50 years, technology companies, technology organizations, right, including companies like IBM, NVIDIA, AMD, and many, many others, have improved our ability to process digital information, to store digital information, and to transmit digital information. I mean, think about it, by 2x every 2 years. That is the reason why we have iPhones. They would have consumed 10 years ago, right, the size of an appliance with many kilowatts. But because of these technology innovations, really the backbone in computation, in storage, in networks, we can do all these things. Now, what have we done with all this technology? Well, we deployed it everywhere, right? It's in our houses, it's in our cars, it's in our infrastructure, and it collects data, it processes data. In essence, it digitizes everything in our lives, in our worlds. Now, what are we doing with all this data? We heard it. We're basically using, interestingly enough, the same advances in technology, in computation, in storage, in networks to exploit all this data. It has given rise to data-driven modelings, where we just have data and we learn models to make better decisions. So now what is important to understand is, in my mind, on this digital journey, right, on this journey to AI, different industries and sectors are at a different stage. And why are they at a different stage? Because arguably certain sectors and industries are easier to digitize, and it's easier then to do subsequent AI and machine learning. So the lagging sectors can actually learn a lot from the leading sectors. So if you think about it, right, the world of media that was way back, right, has been digitized completely and has changed really drastically how we consume media, how we consume movies, etc. So it had a huge impact. So my point here is we digitize the world of media, we digitize the world of business transactions, the financial world. We digitize to a large extent our social worlds. And now we are in full flight digitizing our physical world. And with that, critical infrastructure, weather, the environment, and so on and so forth. So coming back to this question, why GenAI for critical infrastructure? Well, it is because we can. It is because we are now really at a stage where we have more and more data to build more robust models to take advantage of all that. Well, let's talk about AI. Now, I think it's very important. You saw this on my first chart. AI is not new. It has actually been around since the 70s. And we use different words, but at the end, even in the 70s, we had AI in form of what they called expert systems. They were very brittle models, but people tried to build these types of models already in the 70s. And then around the 80s, we have started seeing this rise of big data, more and more data. Maybe not in every industry, right? Think about the different sectors. but we've seen that. And we were able to build sort of task-specific models based on handcrafted features. So we already heard about what features are. Features are sort of variables which drive these models. And so decision trees and simple regression models all fall into this classical age of machine learning. Now then in 2010 around, we had this, maybe some people remember, this Jeopardy moment. Jeopardy, so there was this computer, Brad was there, I was there, in IBM, which actually won the game of Jeopardy against the two all-time champions. And that was achieved with what people call deep learning. And deep learning, all what that means is really we had deeper models, we had neural networks, more complicated models. But the big benefit we got from that is we could actually discover these features which we had to handcraft and build manually. We could do this automatically. So now suddenly we had models which would, given a certain data set, discover the relevant features with respect to a given output, and it was certainly a breakthrough. But then again, all these models were task-specific. One task, next task, task A, task B, task C. And now recently, maybe starting in 2017, we have this age, another paradigm shift, we have this age of foundation models. And foundation models and GenAI is very much related, as I will explain later. But this is the first time where we start seeing models which weren't really built for a specific task, but they were built to be generalizable. They were built to be adaptable to different applications. And how was that possible? It was possible because of massive data that gave rise to this idea of self-supervision. I will explain what that is. We had massive compute. And then in Google, they invented these transformer architectures, which is a certain form of the way you build a model. Now let me explain to you, as part of sort of the mission of this presentation, which is to demystify AI, how actually these foundation models work. How can you think about this? How is it actually possible that they can do all these things? And you ask the questions, etc. So how does it actually work? And you don't have to be an expert to actually understand how it works. It's actually not that complicated. So the best way to understand it is you think about the different steps when you build a ChatGPT type of model, a foundation model. So what's the first step? The first step is you build the actual foundation. So how do you do that? And what you do is you take a very large set of data. Let's say it's text from Wikipedia or text from the Library of Congress or whatever. And then what you say is, you say, well, this is my data. Let me redact, mask. So I take part of the data away. So I mask. And then I have this model, this transformer model, which is right now a black box, but it's an attention network. And I have that model learn what I've masked. So in essence, I create a model which learns what I already know. So some people would think about this and say, this makes no sense. Why on earth would I create a model which predicts what I already know? But the trick here is that through that learning, this model actually captures how language works. It learns that the word coffee is close to the word morning, that the word bagel is close to the word cream cheese. So it learns a notion of language. It learns how language works. It learns how to fill in the blanks of the next word. That's what a foundation model does. Now, all this model can now do is, and you think about it, that is what ChatGPT is based on. All it can do is it can predict a missing word, a missing token, as people say. Now, what can you do now with that? Well, you work all on in different applications and have different problems. But you can take that model, which now has learned a notion of language, and you send that model, so to speak, to college, where it gets fine-tuned. So you specialize it. So there is this fine-tuning step. And what do? Let's say you want this model to be an expert on the Earth software or in power systems. You fine-tune this model, which already knows language, which already knows how to talk, so to speak, how to answer these questions. So you fine-tune it. And then finally, what's the third step? Well, now you have a fine-tuned model. You just operationalize it. Now, there was this question about sensitive data. Now, the foundation model is a foundation. You can take that foundation behind your firewall, and that's a huge advantage because now you can fine-tune it where this model has already learned some of the basics, so you do not have to repeat it. So the key point here to understand, of course, is this pre-training is really what consumes all this power. It's very expensive. That's pretty massive. But then fine-tuning is relatively cheap, and then inference is even cheaper. Although we heard, by the way, I disagree with Claude, although we heard it's more expensive than a Google search. So now let me ask you, because of what I just showed you, now you understand how it works. It's not very complicated. Why is everyone excited about this? And it's on two levels. But the one level is sort of more economically. It is, a lot of AI projects actually in the past failed. It too complicated, took too long, performance wasn't there, was too expensive to maintain these models, blah, blah, blah. And that's true, actually. But now, of course, with this, we have a base. So we have a base model, we have a platform, we have something we can actually start off. We're not starting from scratch every model. Because we have that, we can get away with less labels. Labels is a huge pain, especially in an industry like yours where labels may not be as plentiful. You can get better or similar accuracy, faster development, so economy of scale. That's the reason why so many people are excited. Performance, yes, but it's also a pathway, the first time there is a pathway to better scalability of AI. Now, I want to come back to this interesting aspect of GenAI, these foundation models, that it is just based on a very simple, salient technical feature, which is, right, and I said that, which is this remarkable ability to predict the next token based on context. And that's actually quite powerful. And why is it quite powerful? Well, if I can predict the next word, I can predict the next sentence, I can predict the next paragraph, I can write a book, I can have my model write a full book. So it's quite powerful. But that's not just it. It is because this whole idea of tokens can be extended to different modalities. So a token is not just a piece of text. It could be part of an image. And I can use that same concept, in fact, to convert between different, what people call modalities, between images and text. Let me give you an example. So let's say you have some training data where you have a set of images, and these images are annotated. So you have little descriptions of what in these images are. And of course, as you know, you can now start tokenizing this, where you tokenize, let's say, the first image, you see people in a subway car. There are people, there's a subway car, there's a word, there's the image. You start masking in the same way, we just saw it, across these different modalities. And then you do exactly what I just showed you. You ask a model to reconstruct between the caption and the image. And what does a model learn? Well, it learns how to predict from a caption an image, and if you have an image, it creates your caption. It's that simple. Now, if you really think about this whole idea that you can actually do this modality conversion is actually super powerful, because think about it, when we process data, when we want to make decision, what is that at the end of the day? It's a modality conversion. We have data here, we create a representation, let's say it's a visualization or a dashboard, and then we make a decision. So that is the core of cognition, that is the core of AI, and we have now early evidence that these models can do a superb job in converting these modalities. So to wrap up this part of my presentation, I want you to keep in mind that if you think about foundation models in GenAI, they're really good in this very simple thing, which is next token prediction based on context. And that's really the generative part, the predictive part of this AI. And that is good for gap filling, for forecasting. Think about it. These are all tasks you need if you want to do a forecast. You want to do a prediction of when an asset fails. The second part is these foundation models, that's the foundation model part of the story. They're adaptable, scalable. They're more adaptable and scalable than before. Are they completely scalable and adaptable? I don't think so. But we have made enormous progress to make them more adaptable. And then finally, what is important here is that these models, and that is a property of AI in general, are much faster than what we typically do. They're much faster than compared to simulations we might run on our networks. So they bring you that acceleration. So they're really good in forecasting. They're really good in converting different modalities. That is what we need. They're scalable to some extent at least, or better scalable than what we ever had before. And you can get this massive acceleration. OK. So we heard earlier, right, that these foundation models in form of large language models, which is basically text-centric foundation models, we're using them already everywhere, right? You have them on your phones, et cetera, and they've taken the world by storm, arguably. And they're quite impressive. But of course, that begs the question, how about other domains? Right? How about critical infrastructure? How would that actually, do we actually have foundation models for critical infrastructure? Yes, I can use some of these LLMs to help me with critical infrastructure, but how about all this other data, or these other domains, or these other applications? And can we repeat the successes of foundation models in these other domains? So how would you think about AI foundation model for critical infrastructure? How would you even start thinking about this? Well, one way you could start is, let me have a look at the data. What data do we have actually? And this is for electrical infrastructure, but of course we have weather data, we have load data, we have generation data, we have market data, we have networks, we have SCADA, we have AMI, we have topology. So there's all kinds of data, highly multimodal, certainly not just text, certainly not just images, etc. So it's a zoo of different data sources, right? But just conceptually, you would think, okay, if I could learn the relations between all these different data sources, between weather and loads, and maybe the state of my network, if my model could capture that somehow in the same way it has learned language, then yeah, I can maybe build a foundation model. And so you would imagine that. And then once I have that, conceptually, you would say, great, now I'm going to be able to fine-tune this to all these different applications. Whatever it might be, electrical transient analysis, you might be worried about cyber attacks, outage predictions, vegetation management, etc. So that is how I think about a foundation model for critical infrastructure. Now, I want to break this out into different pieces. And one way you can start thinking about this is you can say, well, maybe we start with something simpler. And let's think about weather. And let's say, and maybe also we think about satellite information. So can I build a foundation model just for weather and maybe satellite data? And so how would you do that? We already know how to do it. We take a weather data set, or we take a satellite data set. We mask, we take something away from this data set, and then we ask that model to fill in the blanks. That's exactly what we show in this image, what we show in the chart. So here on the right side, this weather or satellite data is the easiest way you can think about it is these are different images or matrices. So this could be precipitation or temperature, or it could be a satellite image. And I take pieces away. These are my tokens, these black things there you see within the image. I have this data at different timestamps. I have this data maybe for different channels and layers. I may have it for precipitation, for temperature. I may have it for different hyperspectral bands. And then I take this transformer. Transformers have an encoder and a decoder. And I reconstruct, I teach my model to reconstruct. That's how you build a foundation model for weather. That's how you build a foundation model for satellite data. So not really complicated. So you try to teach that model to fill in the blanks, and you try to teach that model. Oh, sorry. And you try to teach that model, and so that was what we just described. And then you try to teach that model how to reconstruct spatially, temporally, and also across the different channels, the data. So let me give you an example, really real example of how this all works. So we have now built this foundation model, which I showed you on the previous page. And now we want to test it. Right? We want to test, does it actually reconstruct this well? Right? Does it actually can predict missing data? Because that is the core. So here you give this newly trained foundation model incomplete data. And I asked that model, which I just trained, that has never seen this image, to fill in the blanks. And so what do you see in this? You see, I don't know whether you know where this could be. If you look at the satellite image, does anyone have an idea where that could be? No. But the model makes this prediction. I think now it becomes a little clearer where that could be. It's somewhere, whatever, in the Midwest, some agricultural land. So this model, with this very little information, think about it, has never seen that incomplete image, and it figures out, oh, this must be somewhere in the Midwest where you have pivot irrigation, where you see circular fields, and I'm going to make a prediction that what I don't see is actually a circular field and all the other stuff. That's what this model does. Now you can compare it to the ground truth. Very close to the ground truth. Think about it. The model has never seen that, and it's able to fill in missing data. Now I can go even further, and I can say, okay, dear model, why don't I ask you not only to fill in the spatially blocked parts of my image, but also to tell me how this image would look like in 6 months, in 90 days, oh sorry, 90 days. So you're not only taking advantage of this next token prediction skill based on the space, on the spatial information, but also you're making a forecast. And again, it's kind of amazing, this model, based on very little information, knows it's somewhere in the Midwest where you have pivot irrigated fields. It knows that the first image I gave it, which was masked, is somewhere in spring. It knows that there are seasons. The model understands that it can actually make a prediction and predicts the grain, sort of the fall colors of this field. I find it's quite amazing. That's a question.
Yeah. When you mask and ask the model to predict, you assume that all your variables are constant, right? It's not taking into account any like once in a lifetime variables, either whether it.
So it takes into account, it knows the statistics of over, in this case, of over 20 years of satellite observations. So it does not know the weather directly, but it does know how these images looked over time. And so it has that statistics. And because of that statistics, it's actually able to make that prediction. Okay? Now you can also go even further and say, okay, let's say I only have the red band, one band of that satellite. And that band is masked. And now I'm asking the model to forecast me the green band in 90 days based on this incomplete information. And again, the model can do it. So some people might say, oh, but this is all fake, right? These are fake images, predicted. I would say fake is the wrong word here. These are predicted images based on the statistics. It's a forecast. It's a prediction. Of course, it's not the truth. The ground truth you see on the right side, but the predictions are very close to the ground truth. And predictions can be wrong or right. You can check whether they're wrong or right, but in this case, they're remarkably right. But you can do the same thing for weather foundation models. So, we just went through this whole thing. I can have, and we just heard it actually in the earlier presentation, you very often have incomplete data. In this case, in the first image, this is data the model has never seen. I have wind measurements. And you don't see the little dots on this whole globe, but there are a few dots, which I give the model because the masking ratio is very high. It's around 95%. And then I ask that model, hey, fill in the rest, fill in the blanks, which is what these models are really good at. And you can see, fills the whole globe with wind data with quite a lot of accuracy. I can take incomplete precipitation data, ask to fill in the full field, and do a forecast. So that is a spatial and temporal forecasting reconstruction. And then even crazier, I can take wind data, which is incomplete, and ask the model to predict me the precipitation from it. And why does this model can do all that? Because we trained it across all the major dimensions, which is the spatial, the temporal, and the different channels. So it has captured that knowledge. So it knows from incomplete wind information, how will the precipitation look like in a day or 2 or 3 days in the entire globe. So this is all still pre-training. So I showed you 2 foundation model examples, weather and satellite information. I know some of you are working on land use cases, so it might be very relevant. And I know you, of course, the energy industry is heavily weather dependent. So these are some of these AI advances purely learned from data. But how about fine-tuning? Well, you can fine-tune these models, right? I told you very high level, we have these transformers, right? And these transformers, they have 2 pieces. They have an encoder and they have a decoder. And in between, you have this AI representation. But I can just update the decoder to my specific task. So let's say I have satellite data and I want to do wildfire detection. I can take a very little piece, I can take very little training data and have a fine-tuned model detecting wildfires based on satellite data. I can do vegetation management with these in terms of classification, figuring out what, based on satellite information, what is a tree type, and that may help me with vegetation management. I can do asset monitoring. And so these are different examples how you can take that foundation, you can take it behind the firewall, you take some labels, and you have suddenly some real business applications. The same workflow, the same thing applies to weather. I have a weather foundation model. I want to maybe use it for forecasting. I may want to use it for gap filling, but I may want to also use it for hurricane tracking, or I may want to use it for improving the spatial or temporal resolution. I may want to use it for detecting likelihoods of outages, weather data. I want to use it maybe for simple forecasting applications. Same workflows. You don't have to touch this big encoder, which is your foundation model. You can download this in some cases. Some of these models are actually available. You can get them. Take them behind the firewall. You can fine-tune them. So that's a fine-tuning story. Now, how does it actually look like if I really use these models? And so here we're looking at outputs from the weather foundation model. And the first thing, of course, when we do inference, we're kind of interested in potentially how much faster can I actually predict the weather with an AI model versus a traditional weather model. And so here we compare different AI models, not just the foundation model, which I talked about, but even other. Some people might have heard about it. There's a Google AI model, GraphCast it's called, there's a Pangu AI model, etc. But what you see is these AI models are very fast, very efficient once they were pre-trained and fine-tuned for forecasting, creating forecasts for you. You don't need a supercomputer. You can do it on a single GPU. By the way, that is a massive breakthrough. Every weather agency around the globe today is looking into AI emulation for weather forecasts because it's so much more efficient. And because it's so much more efficient, you can do it at higher resolution, and you can create larger ensembles. So it's a gigantic breakthrough. But it's not only that. You look into the performances of these models. So this was an example we published where we tracked Hurricane Ida. And turns out, even for these extreme situations, a lot of people always say, yeah, AI may not work, extreme situations. It's all a question of how you really do that. But, I mean, hurricane is a pretty extreme situation. A lot of the weather data we use to train is actually not hurricane data. But it still does a very good job. What does it suggest? It suggests that this model has indeed learned a notion of how weather works in the same way these models have learned a notion of how language works. And so that's one big conclusion. Now coming back to our foundation model for critical infrastructure. So we talked about the weather foundation model. We talked about the satellite foundation model. But how about, let's say, a foundation model for the network? Right? You all have networks, you all operate networks, at least my understanding, etc. And so how would I do that? A network. But I think you already know how to do it because we went through that, right? So what do you need to do? Well, you know, a network, of course, as you guys know, can be represented, it's a graph. People in computer science would say it's a graph. And the graph has nodes and edges, right? The edges could be the pipelines or power lines, and then the edges or a transformer, and then the different nodes could be load buses or generation buses, etc. And of course, the network has state variables. In the electrical case, there may be power, active power, reactive power, the voltages, the angles. Gas network's going to have other state variables. And then I do the same thing I learned just before. I take something away from these large data sets. Now I assume I have this data, but sometimes you can generate these data sets. And then I have a model which learns to predict from missing data the rest of the data, which predicts all these different tokens. It's basically a model which can predict state variables based on some other state variables. That's what I'm creating here. In the electrical world, right, for power grids, that's a standard thing people do. It's called power flow or load flow. But this is what this AI model would do. It would do exactly what today a traditional power flow solver would do. It would basically tell you what are the voltages on the different buses, right? What are the powers, the reactive and the passive power, what are the phases, what are the loading on the different lines, etc. Now, of course, you know why these simulations of your network are important, I would assume, right? Because that's the only way you can actually avoid something like this, right? This is the gigantic Spanish outage they just had, which were all caused by lacks of oversight, but at the end, lack of preparedness through simulations of different situations in the electric grid that caused this. I think it lasted many hours before they got this back on. So so we actually developed this type of foundation model for the electric grid. And so I want to just show sort of high level what this does. What it does, what does this model actually add to what we are doing already today when we look at different networks? And if you think about it, you want to simulate a network, you want to have good accuracy, right? If you simulate it, you want good accuracy for sure. You need it fast because you don't want what you just saw in Spain happening. So you want to be able to run lots of simulations, so very fast. You want to do this efficient with very little data because you may not have all this data. And of course, networks, they have this tendency, they change all the time. So you want to do it so it is robust against network changes. So if you look into the traditional techniques which we have, they're great in data efficiency. They're great in dealing with topology robustness. They're great in terms of accuracy, but they're lousily slow. So bespoke AI before foundation models, was already very fast, was very accurate, but unfortunately wasn't really efficient with data, needed a lot of data, and also it wasn't really topology robust. So now these foundation models is really the first time where we have network AI emulators which are accurate, which are robust against topology changes. So if your network changes, you don't have to rebuild a completely new model, etc., which are very fast. And because they're foundation models, you don't need a lot of data to train them. Okay, so what can you do now with such a network model? So now I have a network model, which is very fast. How does it really help me? So for example, here, we are showing for the Texas grid, the ERCOT grid, electric grid, contingencies, right? As you know, in the electrical networks, they have contingencies. If something fails, they call it N-1 because one thing can fail, one line can fail, one generator can fail, etc. So they call them N-1. Today, everything we do when we plan for contingencies in the electrical network is for N-1. Partially because that is what the regulator actually asks us to do, but the main reason why we're doing N-1 is because that's all we can do. That's really the reason why we're doing N-1. We cannot calculate N-2. In fact, if you look back into the Spain situation, one of the reasons were exactly that they weren't prepared for more than one outage, for more than one disruption. So here's an example where we show, and I don't want you guys to go through all these details, but where we show within seconds, we can actually run N-2, which is, of course, an exponentially numbers of scenarios because we have now an AI emulator. And that AI emulator is actually accurate. And how do we know it's accurate? Because we can check actually on the actual power flow equation. So we actually know it's accurate. And we can do this for these different grid topologies. Another area where we have applied these accelerated network models is this question we talked already this morning about is, how on earth can you power all these different data centers? So one interesting aspect is, of course, when you When you have a new project, a new data center, or even a new renewable energy farm, you got to be connected. In some cases, you have choices about where you can connect. Today, we don't know beforehand what are, out of all the scenarios you can have, out of all these load buses in Texas, in reality, you have 7,500 different load buses you could connect to. And then you have multiple load scenarios you need to run. You have multiple contingencies. What is the best place to connect your new load? What is the best place to connect all your renewables, assuming you have actually the ability to produce a renewable energy there? So it's a way to figure out how you plan your grid. It's a much better way to figure out how can I accommodate new load, new generation, without massive infrastructure investment. So it's a real opportunity. So let me come to my final chart, and I hope then you have a lot of questions. So I've thought, I think it's really important to, in my mind, to demystify AI and GenAI. I think actually AI and GenAI are very unfortunate words because they imply something which isn't really, in my mind, real. Predictive AI would be better, and AI, I have my problems. But it's not a miracle. AI is definitely not a miracle. It's a logical result of 50, 60 years of improvements in technology. And it's remarkably consistent. The improvements we've seen in the underlying technologies have been remarkably consistent. Maybe quantum computing comes along that day, but it's a logical result of all that, and that's why we are now in this situation. And of course, different industries experience these disruptions, if you want to think about them as disruptions, at different stages, and that has to do with the complexity of the industry in terms of digitization. So I do believe GenAI gonna advance massively. There was this question, I think, what would be our role in the future? I would choose, right, I think Johnny Cash said once, you can choose love or hate or something like that. You can choose optimism. I would choose optimism here too. AI going to do a lot of the mechanical work, and they're going to do an excellent job, but we still need to design the systems. We still need to conceptualize them. We still need to figure out what we want that AI to do. So I think it's actually quite exciting. The other key point is GenAI is, again, this word fake in my mind. Sure, you can create fake images, you can create fake things, but if you do a prediction, so always think about it. In many cases, GenAI is being used for predictions. In the same way we do forecast or customer forecast. And we are not calling these forecasts fake just because they're predictions. So I think it's really important to distinguish between that. And then I would finally say, of course, don't fall for the hype. But I also would say don't underestimate what GenAI can do for you and will do for you in the future. Thank you.
I noticed there's a tiny word just past physical. Curious what that is, or if maybe you can say what is digitized after physical. That's what
There is a tiny word.
Yeah, or is it a dot?
It's a dot.
So, but then kind of coming back to that, do we know, is there something that would be hypothetically digitized after physical? Is that your sequence here?
So how about space, right? That would be my answer. We're already seeing a lot of that, right? And I think, by the way, thanks for the question. This digitization, right? I hear a lot of people saying, especially in your industry in general, saying, "Oh, I don't have enough data, right? I can't do that. Oh, we're not ready for AI." But then remember this digitization of our physical assets and everything we do. We made enormous progress, but frankly, we're just at the beginning of it. but it's also exponentially accelerating, right? I had on one of my charts saying that 90% of all data was generated in the last 2 years. So if you don't have enough data right now, just wait a couple of months, you may have it then, right? So I think that is that's something to keep in mind, right? As you think about what happens in 12 months, I think you're gonna have much more access to data, right? Think about this 90% of all data generated in the 2 years. That may not be quite true for this industry yet, but I think we're getting there. And so that is, and I think that also impacts your AI strategy, right? It impacts how you want to think about it, what investments you want to make, where do you want to really focus on with AI skills and all that kind of stuff. Yes, first year, then you. Okay.
So how would you use standard tools for the average person that may not be a data scientist, something like Copilot, to build these foundational models?
So I think, for example, the fine-tuning, right? The fine-tuning is actually quite simple. And so, for example, the weather foundation model, let's say that's what you wanted to do. And you want to say, I'm not a data science sweatshop and so on and so forth, but I want to do something with that, right? There are actually examples which show how to use these models for specific applications, how you fine-tune them. And you would be surprised how simple these examples are. They are literally 150 lines of code. They're not really complicated. Today, a lot of these examples come even with these online notebooks like Colab. You just click on the link, it spins up an environment, you can execute it there. So, or of course you hire people, but I would personally say there's a lot you can do if you sit down for half an hour, or if you for an afternoon, and really look into some of these examples and see how these examples have been applied, and then you say, oh, how does that actually apply to my business? So this is what I want to do. And I think that would be my recommendation. And these foundation models, I mean, think about it. They're not built to make your life harder, right? They're actually built to do the opposite, to make it easier for people so they don't have to create these massive data sets to train these models you build on top of something which is already being built. So I think that whole trend, that's why people are excited also about it. This whole trend is actually a good one. Was the second question here?
Maybe a little similar, but how accessible would you say these models or this process is to an average engineer or a small team that has an idea for their product or whatever the application may be?
Yeah, let me repeat that question. It was very similar to the previous one, right, which is about how accessible are all these models. I think if there's one thing we learned over the, I would say maybe last 25 years in technology is that open source has actually made a huge impact and was actually a winning strategy for many. So to get started, and I'm not suggesting you want to base your business on open source, but to get started, to understand whether things can actually help you, you want to start with these open source models. All these models I talked about, the weather foundation model, the satellite foundation model, and even the grid foundation model, they're open source. You can find a version of that with open source. You can find a version with that with examples. You can find a version of that where we actually run through contingency analysis, or where we do downscaling, or we do hurricane forecasting. So I would say that's the way I would start. I would start with the open source and see what this technology can really do. And then once I know and understand what it actually does, then yeah, maybe you want a license, get a commercial license, etc. But that's what